In the realm of industrial automation, every organization generates a vast amount of data at an exponential rate. This data includes transactions, customer interactions, system logs, emails, and support tickets. Despite the continuous accumulation, a significant portion of this information remains untapped and unanalyzed, often referred to as being in a state of data dormancy. This situation presents a paradox in the age of data-driven decision-making. Imagine a treasure chest filled with valuable gems, yet no one has the key to unlock it. Machine learning offers that key, providing the tools to extract valuable insights from these dormant datasets. By applying ML algorithms, organizations can uncover patterns, predict outcomes, and optimize processes that were previously hidden within their data repositories. And here's why that matters. Machine learning algorithms are the secret sauce that transforms dormant data into strategic assets. Imagine these algorithms as highly skilled detectives, sifting through mountains of data to uncover hidden patterns and correlations. They operate on the principle of learning from examples, which means they get better over time as they process more data. For instance, a supervised learning algorithm might be trained on historical PLC data to predict machine failures. It learns from past instances where machines failed and the conditions that preceded those failures. Once trained, it can then analyze real-time data to predict future failures with high accuracy. This predictive capability allows for proactive maintenance, reducing downtime and saving costs. But there's more. Unsupervised learning algorithms can identify clusters within the data, revealing groups of similar operational conditions or behaviors. This can lead to insights about process optimizations that might not be immediately obvious. Think of it as finding the hidden gems within your data mine. To begin integrating machine learning into your industrial automation systems, the first step is configuring your environment. Start by selecting a robust integrated development environment (IDE) that supports machine learning libraries. Install necessary packages such as TensorFlow or PyTorch. Ensure your PLCs are equipped with data logging capabilities. Next, establish a data pipeline that collects and preprocesses data from your PLCs. This involves setting up data acquisition modules and ensuring they communicate effectively with your IDE. Remember, the quality of your data pipeline directly impacts the performance of your machine learning models. For optimal results, normalize and clean your data before feeding it into your models. Consider this: your data pipeline is the fuel line to your ML engine. Make sure it's efficient and clean. Now, let's delve into the execution of machine learning within industrial automation processes. Picture this: your programmable logic controllers, or PLCs, continuously gather operational data. To transform this data into actionable insights, you'll need to integrate machine learning algorithms directly into your automation workflows. Start by selecting an appropriate machine learning model. Consider a predictive maintenance model for anticipating equipment failures. Next, pre-process your data to ensure it's clean and formatted correctly for the algorithm. This involves normalizing values and handling missing data. Then, train your model using historical data from your PLCs. Set specific parameters like learning rate and batch size to optimize performance. Once trained, deploy the model within your automation environment. Monitor its predictions and adjust parameters as needed to enhance accuracy. Remember, the key is continuous learning and adaptation. This approach not only improves operational efficiency but also minimizes downtime and reduces costs. Now, let's dive into advanced techniques for optimizing machine learning applications within industrial automation. One key strategy is hyperparameter tuning. By adjusting parameters like learning rate, batch size, and number of epochs, you can significantly enhance model performance. For instance, setting the learning rate too high can cause the model to overshoot the optimal solution, while too low can result in slow convergence. A balanced approach often yields the best results. Another critical aspect is feature engineering. Selecting the right features and transforming them appropriately can lead to more accurate predictions. Consider using techniques like one-hot encoding for categorical variables or normalization for numerical data. Additionally, Ensemble methods can be employed to improve model robustness. By combining predictions from multiple models, you can achieve higher accuracy and reliability. Remember, the goal is to extract the maximum value from your data, so don't shy away from experimenting with different approaches. And here's why that matters. When integrating machine learning into industrial automation, several common pitfalls can derail your efforts. First, be wary of overfitting. This occurs when your ML model performs exceptionally well on training data but fails to generalize to new, unseen data. To combat this, always validate your models using a separate test dataset. Next, data quality is paramount. Garbage in, garbage out. If your input data is noisy or inconsistent, your ML outcomes will be too. Implement robust data cleaning and pre-processing steps. Another pitfall is ignoring domain knowledge. ML is not a silver bullet, it must be informed by the specific context of your industrial processes. Collaborate closely with domain experts to ensure your models are relevant and effective. Lastly, be cautious of algorithmic bias. ML models can inherit and even amplify biases present in the training data. Regularly audit your models for fairness and equity. By being mindful of these pitfalls, you'll ensure a smoother and more effective ML integration.